So I'm going to take this implied volatility code. Again, it's based in Leisen Reimer, and the original code we obtained from Fabrice Roua, and so I'm just going to take the code here and set it up. Because it's a single script, it's easy enough to transfer over to an online compiler. And just basically I'm going to try and replicate the results that I had obtained in the previous video clip. So I'm taking the code out of Visual Studio, and then I'm going back into an online compiler, which I have here. I'm using this online GBD, but there's others as well, and we'll just paste, and goes in without too many issues. And I'm assuming that we have the same parameters here as before, and if you like, the origins of these parameters is again based on Brody the Temple, and we're using this table 1, page 1, 2, 2, 3 from Brody the Temple, and the original article here is, go counterclockwise, is Brody the Temple 1996 Review Financial Studies, Volume 9. Okay, so let's go back to Table 1 then, where the Table 1 we have I just rotate this. Table 1 here, we take just a few values. We're going to take this middle value where the stock price is 100. We're looking at call options. Stock price is 100. The exercise price is 100. The market value, or the price we observe, is 4783. And what I want to do is use Leisen Reimer to obtain the volatility implied by the, if you like, the market price. So this is a model price, or we might observe it in the market as 4783. We've all the other parameters, except we don't know what the volatility is. We're looking to deduce the volatility, and we're hoping to find that the volatility would be 20%. Okay, so basically the parameters that we have are the stock price is 100. We can just bring it up here on our screen for a second. So the stock price, we're saying, is equal to 100, the exercise 100. The maturity is equal to 0.5 years, risk rate 3, dividend is 7, and we're seeding our initial guess in this bisection technique to be, the low ball guess is almost 0, and the high ball guess for the volatility is 7%, and then we apply this bisection technique to triangulate what the implied volatility is. So 4783 corresponds to the 4783 here, and what we want to deduce is what's the volatility consistent with these other parameters. Okay, so let's go back into our code and just execute. We should get roughly 20%, and we get this 200032. Now that's on a step size of 100. We could probably increase that to 1000. If we do, again, it's going to take a lot longer than before. It's now 1333. I'm going to stop. Actually, it has estimated, and it's slightly more accurate. We could go maybe 2000 steps. This probably is not. So okay, so 2000. Let's just look at the impact of doing that. How much slower is the execution of the bisection technique when we increase the number of steps to 2000? Keep in mind, when we do raise the number of steps to 2000, the estimation taking place is doing a kind of a grid search. So there are these initial values for the volatility. the A is this low value, the B is this high value, and we have to keep going through a sequence of re-estimations until the 0.001 converges with the 7, and that actually is being pulled out of this bisection technique, which I've explained in the 2 additional videos later. But the bisection technique is basically taking the market price and subtracting away the model price, and we're trying to reach within a particular tolerance level convergence. Again, by increasing to 2000, we're not getting a real big bump up in level of accuracy here, so 1000 probably is fine. We can try that again. We run. We can observe the time taken to run the estimation, and it takes longer obviously than the 100. We can check in a second what the estimation time involved is. It's okay, so a small bump up was a bit quicker. Okay, so we could add in some actual times here by including a small bit of code. We might do that now. So I'm going to add in a small bit of C++ code here to track the estimation time. Okay, so we've this clock. We can take out the pause. That's not required, just used for Visual Studio. I need also, so I'll make paste in an additional little bit of code. We just put that in after main here in the value. So let's just do a little bit of paste. So we start the clock, we do a start the clock, and then we have to end the clock and report the value in seconds. And I need to also include another small snippet of code, so include it up at the header files. We'll just make a little bit of space after the CMAT. We'll just paste in this library, include this library. Okay, and we'll run the estimation again. I'll reduce the number of steps down to 10. That's fairly low. Okay, so let's run, and we have to have 129. Let's just see where there's a small error in the estimation. So I'll pause and correct the error. Okay, so it was a very tiny issue. It just related to including a semicolon that I'd left out in the copy and paste here, but otherwise it's running. So if I take 10 steps and run the estimation, it's taking, we can see, a trivial amount of seconds. If I raise that to 100 and run again, the amount of time it takes will increase. So now it's 0.02 of a second. If I increase that another 10-fold, so another 0 put in, and 1, so 1000 steps in this bisection, so Leisen Reimer Implied Volatility using a bisection, we can see the number of seconds is going to increase, and there's a more than 10-fold increase. So we increased the number of steps. Okay, we're now up to 3 seconds, and if we go to 2000 steps, so I'll delete. So it takes 3 seconds to run for 1000 steps, and again a number of estimations have to be performed. That's 2000. I expect this to go above 6 seconds now in this latest run, because the estimation increases exponentially with the number of steps, partially because the binomial model, as you increase the number of steps, the number of nodes grow, but also take into account we are triangulating, or we're trying to estimate the implied volatility using a low value and a high value, and these values are being adjusted. So okay, the results are here. 11 seconds, 11.2861 seconds. So we've jumped from 3 to 11 by doubling the number of steps. Still okay. to do it this way, it's not bad. It's a relatively fast estimation, relatively nimble, probably commercially on a trading platform. The latency of 11 seconds though would be excessive, but for purely estimations that we want to verify in any kind of academic type of research, this probably is feasible enough. That latency in the estimation is not excessive. It's about right. Okay, so I will share the code. I just come up here to share, and then the code that I have here on the online compiler, I'll include that link underneath the video clip in YouTube.